welcome back to the Red Door Analytics online course, Survival Analysis, an Introduction to Concepts, Methods and Software. In this part of the course, we will be talking about survival. So survival, also denoted here as ST, is a very important measure in survival analysis, is the survival proportion, which is here defined as the function S as a function of T, which is equal to the probability that capital T, which is our event, is greater than small t. So this is the proportion of study subjects at time t who have not yet experienced the event, where capital T is the event time and it's a random variable. So the value ST, or the survival proportion, is commonly presented graphically via the Kaplan-Meier curve. This presents the survival proportion across the follow-up time using the Kaplan-Meier estimator. Note that you can also estimate the survival proportion using other methods. This is just one of the most commonly ways of presenting survival proportion. So the survival at time t is estimated in the following way via the Kaplan-Meier estimator. So we look at survival time at time 1 here, which would be equal to the survival at time 0 multiplied by the number at risk, n, at time 1, minus the number of events, which is represented by D at time 1, and divided by the number of events at time 1. And then what we can do is we can look at what happens at time point 2, and we basically go up this iterative process using this formula to get to the point where we can see that the formula is as presented here on this line. So it's basically a function of the previous survival proportion, the number of events at that time point, and the number of at risk at the time point as well. So if we go back to our study example, which is looking at breast cancer recurrence or death of patients with breast cancer in Germany, then we can look at the survival proportions at every time point, at least where there is a censoring or an event, by using Stata and the SDS list command. So if we just write out SDS list, you can see we get this output here. So at every time point where there is a censoring event or an event of interest, we basically get a survivor function. So you can see that we have time here represented, we have the number at risk, we have the number of failures, and we have the survivor function, which is the probability of surviving up until that time point. So we can see that the first individual that is censored, so we have failure is equal to 0 here, at time 0.02, and remember that we have ST set in Stata to say that our survival time is in years, so this is 0.02 years. We can see that actually the survival function is still 1 because no one has yet had an event of interest. And if we continue down our list here, you can see that the first around, how many observations is that? Maybe 10 observations actually do not have any failure. So we have the same survival function for a little bit of time up until 0.19 years, at which point we actually do observe a failure. So we have an individual where 672 individuals are currently at risk. One person does die or have a recurrence of cancer at time 0.197 years. So if you were to use the formula that I previously presented in the slide, you would see that this ends up as being the probability of surviving of 0.9985 at this time point. And we use this formula to go down each of these times at which we have a censoring or an event and recalculate the survival probability. So then we can plot this. So here we have a Kaplan-Meier plot. It's a very typical plot to see in any survival analysis study. We have the survival proportion on the y-axis, and then we have on the x-axis here, always the time scale. In this example, it's time since breast cancer diagnosis because we're still looking at our study example. And we've also put in the bottom the number at risk here. So you can see at each of the years, how many people are still at risk. And you can see from this how the survival probability decreases across this time scale. So each of the drops here represent an event, so either a death or recurrence within our data set. We can see that this doesn't go down to 0 because we have censored observations. Not everyone experiences the event within our time frame. So here's the code for the graph if you want to replicate that. We use the SDS graph command. There's lots of options here that you don't necessarily need just to make it look nice. But basically you need the SDS graph command. So we said before that we were interested in looking at this variable hormonal therapy. So we may want to look at the survival curves, the Kaplan-Meier survival curves by hormonal therapy, and we can do that using SDS graph again. And we can get a plot that looks something like this, where again we have the survival proportion here on the y-axis, the time since breast cancer diagnosis in years on the y-axis. We have two different curves now which represent different hormonal therapy groups. The orange curve represents hormonal therapy, and we see that the survival is higher in this group. And then the blue curve here represents the no therapy group. And at the bottom of the curve, we've also presented the number at risk at each of the year points across our follow-up time. So what we could conclude from this is that we see that taking hormonal therapy seems to increase the proportion of patients surviving. We can see that that curve lies above the no therapy curve. And here again is the code for the hormonal therapy graph. The main part of the code is this first line here, where we have SDS graph by hormone, and then we have lots of other options that you do not necessarily need. One other thing that's commonly presented is the median survival time. So this could be interesting, and it basically is when the probability of survival is 0.5. And we can do this in Stata using the SDCI command. So here we state SDCI, and then we want to say, let's look at this by hormonal therapy. So we won't get an overall value, or we will, as you can see from the output, but we'll also look at the median survival in the two groups. And we can see from this output that we have a number of subjects in each of the groups. So we can see that. And then this 50% here presents the median survival time in each group. So the median survival time of those with no therapy is 4.18 years. And the median survival time in those that have received therapy is 5.53 years. And we have the total value across the whole of the individuals here at 4.95 years. And what does this look like on our curve? Well, what we can do is we can say, okay, the median survival is when survival proportion is 0.5. Well, let's go across and see where these hit the curves. So for the no therapy group, we see that this is 4 point something, and that's the value that we got in our previous slide, 4.18. And if we continue across to where it hits the hormonal therapy, we see that it's about 5.5, which is what we saw in the output from SDCI in the previous slide. So one other way to present the survival proportion is to present actually the complement of the survival proportion, which is called the failure function. So it's just 1 minus the probability of survival, or it could be the cumulative distribution function. This denotes the probability of the event by time t and not the survival of the event. So if we go back to our example here, we would have the probability of death or reoccurrence on the y-axis here, and then across our timescale, time since breast cancer diagnosis. And we can see that this curve is increasing in exactly the same shape as the previous curve, the Kaplan-Meier, was decreasing. So we would just see, instead of having the probability of survival, the probability of death or reoccurrence. So at around 2 years after breast cancer diagnosis, the probability of surviving, the probability of death or recurrence is around 0.25. Here's the code for that function. We again use the SDS graph command with the option for failure. So one thing that might be of interest is testing for differences in the survival proportion. It's common to be interested in determining whether one group has better survival or lower risk of the event than another group. For example, does a new treatment on the market have a better survival than a placebo? So what we can do if we want to look at differences in survival is we can start by just looking at the Kaplan-Meier curve. We take our study example of hormonal therapy versus no hormonal therapy on the recurrence or death after a diagnosis of breast cancer. We can see that, well, yeah, there seems to be a difference between these two curves, but we don't know if that's statistically significant at this time point. So what we can use is something called the log rank test. It's a common method for testing for differences in survival proportions. In fact, what it does in the background is it tests the quality of hazard rates in each group by comparing the observed and expected number of events at each time point. The expected number of events are calculated under the null hypothesis that the hazard rates are the same in each of the groups. So in Stata, this is easily done by using the SDS test command. Here we use that, we say SDS test and we say hormone because we're interested in testing whether we have the same survival in the hormonal group therapy and the no hormonal group therapy. And we can see here we get this output here where we have the number of observed events, and then in the background expected events are calculated. And we compare this to a chi-square distribution. And we get a p-value of 0.0034. So this means that we should reject the null hypothesis that the survival in the two groups is the same. Hence, we see that there is a significant difference between the survival in the hormonal therapy and the non-hormonal therapy. So a natural thing might be to say, well, why didn't we just stop at this? We already see that there's a difference between the two groups. Well, I think it's really important at this point to just mention confounders. We don't know if there's confounders of this association between hormonal therapy and recurrence or death that could be affecting the difference between these two groups. So this is one of the reasons why we go on to modeling. So that's it for this section. Here's some further reading. If you're interested in reading more about the log rank test and the methods behind that, there is a reference here and some other references. And I'll see you in the next section.